Alrighty, guys, can you hear me again?
Yes, we can hear you.
So this was forwards, right? So the next thing is going to be futures, and so there are differences and there are similarities. In some ways, futures are more involved than forwards, and in some ways they're not. And in the end, we derived this formula here that said that the forward price was given as a conditional expectation. The same thing is going to be true with futures. The thing to keep in mind is that they're going to be expectations under different measures. So sometimes they will be the same, but all the times that we're interested in, they're going to be different. And I have an example prepared where they show that they're clearly different. They're not going to be the same. Right, so yes, futures and forwards can be the same. They can have the same price, but most of the time this is not going to be the case. And as soon as you have stochastic interest rates, you should not expect these two quantities to be the same. And then you can ask, like, so which one is then going to be more expensive? Okay, so that's what that problem is about. So what we're going to do now is I'm going to take you through how this formula we're going to get for the futures price, right? And it's going to look, in the end, it's going to look very, very similar to the forward price we just derived. But the detail, the crucial detail is that it's going to be on a different measure. Right? And these two measures are going to be different, and therefore the two prices are going to be different. So we already have talked about futures as well, even though it's been a while since we did it. Yeah. So let's talk about futures and try to derive an expression for the futures price. We're switching into futures now. But it's going to be the same thing. So at the end, we're going to be so now we're going to be looking for a futures price process. And it's like with the forward, the word price here, this is quite misleading. We're going to be looking for a futures price process. We're going to denote it by phi, and then the price is going to run from current time up to some capital N. So the period is over. The final payment date for the futures is here at the end, capital N, and we're sitting here at some little n, right? And then there's going to be payment dates in here. So at the end, when m is equal to capital N, phi is pinned down by n. It's going to be this Zoom is very in trouble here. Phi is going to be that Sn. This is the underlying. So at the end, that's how it's going to be. So now, what about at earlier times? Well, at earlier times, there are going to be these payments. So there's going to be this marking payments depending on how the futures price has changed. Okay, so let me try to go through how would one. So what about at earlier times? What about when m is less than capital A? What is phi then? In particular, what happens when m is equal to 0? Well, let's say that we add time n. So that's the very beginning. What we're going to do is we're going to invest this phi. We're trying to figure out what phi is. Okay, so invest this into the bank. And then we're going to buy, and we're going to go long. So go long. We're going to go long 1 plus Rn futures. Remember, buying here, futures are free to enter. But if we enter a futures contract, we're going to be facing future payments at all these time points after N, right? And the thing that determines how much we have to pay is this futures price that we're trying to determine. So this is what we do at time little n, where we have this amount of money, we're going to put it into the bank, right? And then we're going to buy this amount of futures. Buy meaning go long. So then at time n plus 1, something happens, right? At time n plus 1, in the bank, we invested that much at the earlier time, so we're going to have that much times 1 plus Rn in the bank. Remember, the interest rate Rn is what works from n to n plus 1. So we have this much in the bank, and then we have to deal with these futures. So we have this marking to market. We're going to receive, and this is because we're long. We want to receive how many futures do we have? Well, we have 1 plus Rn. That's the number, and then the price, the change in the futures price. Phi n plus 1 minus phi n. This is the change in futures price. Right, so that this was the fair futures price at time n. This is the fair futures price at time n plus 1. Right, so this is how much we have, right? And then we're gonna get this payment. We add the two together. We're gonna add the two together. So we're gonna deposit. We're gonna deposit 1 plus Rn times phi n plus 1 minus phi n in the bank. Right, so we're gonna have a net bank. We're gonna have a net bank of being this quantity plus that quantity. Okay, we can see there's a minus sign here and there's a plus sign here. So it will be net bank will be 1 plus Rn times phi n plus 1. So what else to do? Well, we're going to enter more. We're going to buy more futures. So the overall futures position is like, how many do we have? We already have 1 plus Rn. We're going to change the position so that the overall position, buy or sell more futures, so that the overall position is 1 plus Rn times 1 plus Rn plus 1. We can do this at no cost. Okay, so what we have now here at time n plus 1 is that we have a net bank balance of 1 plus Rn times phi n plus 1, and we are long 1 plus Rn times 1 plus Rn plus 1 futures. Okay, so now we move up at the next time at n plus 2. At n plus 2, then what happens? Well, we have this stuff in our bank that was there at time n plus 1, so we're going to earn interest. So we're going to have in the bank, we're going to have 1 plus Rn times phi n plus 1 times the new interest rate, Rn plus 1. And then we have, that was our bank, right? And we're going to have a payment, the number of futures, 1 plus Rn, but now it's 1 plus Rn times 1 plus Rn plus 1. So we're going to get a payment. We're going to receive the quantity, 1 plus Rn times 1 plus Rn plus 1. And then the futures price, phi n plus 1, n plus 2 minus phi n plus 1. So this is what we're going to receive. And we're going to put it in the bank. Deposit in bank. So that's going to give us net bank. you add this quantity and that quantity together, and you can see this one here comes with a minus sign. So net bank will be 1 plus Rn times 1 plus Rn plus 1 times phi n plus 2. Okay, and then we keep doing this. We're gonna change the futures. We're gonna change the futures position to be buy or sell futures. So overall futures position is what would be 1 plus Rn times 1 plus Rn plus 1 times 1 plus Rn plus 2. And then you keep doing this, so you can see the pattern now. This keeps going all the way. So we started here time n all the way up to time n plus 2, then n plus 3, and so on. And you can see the key thing here is that this is how the net bank balance evolves. So when we go forward like that, we're going to end up at time capital N. We're going to have a net bank. We're going to have a net bank, which is going to be these ones here all the way up to time capital N times phi capital N. So we have the net bank will be 1 plus Rn, 1 plus Rn plus 1, 1 plus Rn plus 2, all the way up to 1 plus Rn minus 1 times phi n. But remember the terminal condition. It was pinned down here at the end. This was the underlying securities price. At the end, this was my Sn. So this quantity here, this is Sn. Right. So we started out by investing phi n dollars into the bank, and then we went along with this procedure, and we end up with this amount in the bank. Right, so we don't know that the price of this payoff, the price of this year is at n for this payoff, which is coming at capital N. This is what? This is the conditional expectation, and then you discount it. You discount it back to time little n using the money market account times the payoff. So this is 1 plus Rn, 1 plus Rn plus 1, all the way up to the n, and instead of phi n, I'll write Sn here. And then the condition. You can see that ratio we have Sn over S capital N. This is exactly these interest rates here. So this expectation here, this is nothing else than the expectation of Sn given Fn. Right, and what is the price? Well, what did it cost to enter? This was phi n. So this is our new formula. Phi n, this is the futures price, is given as a conditional expectation. Right, so we also had the forward. The forward was Fn was equal to a conditional expectation, but not under the risk neutral measure, but under the forward measure of Sn given Fn. So you see, this is that's the forward price, right? And this one here, this is the futures price. So they have very similar expressions. The only difference is this expectation that you're computing. Is it under the risk neutral measure or is it under the forward measure? If it's under the forward measure, you're going to get the forward price. If it's under the risk neutral measure, you're going to get the futures price. And so again, as we talked about before the break, when P tilde n is equal to P tilde, we will also have that phi n is equal to Fn. right? And this here happens when you have non-random interest rates. So this is, for example, when Rn is not random. So I wanted to take you guys through a couple of problems where we're looking at futures. Are there any questions before I start solving another problem? The first problem I want to have a look at is number 8. Let's try to bring up problem number 8. So problem number 8. So what's going on here is that you have, again, a stochastic interest rate model. We have the usual IIDs, you call epsilon here, and we're going long a futures. And so we have these payments that are determined by the change in futures prices, and we're given the terminal condition that at the end, this is a futures contract that's written on an interest rate. So our job is to work out what is FK, what are the futures prices. And there's a hint here that you should write them in this form. It's a constant AK plus another constant BK times the current interest rate. And our job is to find a recursion for these coefficients AK and BK, just like we did before the break. But before the break, we did it for a forward. Now we are asked to do it for a futures contract. Okay, so how do we work it out? Well, there's this conditional expectation that has to be computed. So let me just copy the model. It's the Rn plus 1. It is that formula for the interest rate that is going to drive everything. And this is, in this model, is given as the next one is given as 1 plus the previous one times times these coin flips, epsilon n, the IID, and they go up and down with U and D and P tilde, 1 minus P tilde. Our job is to find that the forward price, the futures price at time K is going to be a linear, an affine function of the current interest rate. So this here is the futures price at time K. At the terminal one is pinned down, Fn, this is pinned down to be Rn. And so what we do is you're going to use that formula we just derived. Our job is going to be to calculate this conditional expectation here. Our job is going to be to calculate. So our job is the conditional expectation now under the risk neutral measure of Rn given Fk, if you want to get Fk. And so to get a feeling for it, just like before, we could start out like, how does one come up with this guess? Well, we could start by going just one back. We could start by saying, let's just compute the conditional expectation one step back, just as we did before. And how would one go about doing that? Well, you take the expression up here. So you need the interest rate at the end. That's this guy. Okay, so we needed one earlier. 1 plus Rn minus 1. And then you need these independent coin flips. This is epsilon n given Fn minus 1. And so what we end up with is 1 plus in minus 1. This is measurable. He goes outside. And then this one is independent because of the IID assumption. So let's work out what this expectation there is. This will be 1 plus Rn minus 1. And then this will be P tilde U plus 1 minus P tilde D. So you can see this is an affine function of Rn minus 1, right? This here is really of the form, what is it called? The coefficients up here, you will call A. So this is of the form A n minus 1 plus B n minus 1 times Rn minus 1, right? And you can match up coefficients. Can match up coefficients. So the A n minus 1 is going to be, well, it's going to be this one over there. And B is going to be the same. So this is quite similar to the problem we had before the break, but it's always, when you start out solving a problem, it's not a bad idea just to do it one step back before you do the general. So more generally, what is it going to be? More generally, it's going to be like if I wanted to match up coefficients here at the very end, I'll have to have that an is equal to 0. I have to have that an is equal to 0. I have to have that bn is equal to bn. That should be a 1 then. So that's at the end. And then what do we do? What do we do at earlier times? Well, at earlier times, it's the usual story. We will have to have, say, an plus bn rn, right? You want to have that this is equal to the conditional expectation of rn given fn. And then we can use iterated expectations. We plug in a conditional expectation, and this is all under the tilde measure. So we plug in fn plus 1 given fn, and then I'll have rn in here. Right, and now the inner one, we're pretending like we have that property at that time n plus 1. So here we will have a n plus 1 plus b n plus 1, and then r n plus 1. Right, so here comes a time where we need to match them up. Right, to an is of course a constant. We don't have to compute expectation. Bn is a constant. You go outside. So what is really left to compute is this rn plus 1. So this is an plus 1 plus bn plus 1 times, and then this rn plus 1 given fn. And this calculation here, this is very, very similar to the one that we just did for warm-up. But let's do it one more time. So this is equal to an plus 1 plus bn plus 1. And then what we do is we insert rn plus 1. That was given in the problem. So we insert what this is. This is 1 plus rn epsilon n plus 1 given fn. So this is good because he is independent of that one, and this part here is measurable. He travels outside. 1 plus rn, right? And then the expectation of epsilon n plus 1. And this we can work out exactly as we did before. This will be p tilde u plus 1 minus p tilde d. Okay, and then we collect terms. We will have constant coefficients. There will be the an plus 1. And then there'll be a bn plus 1 times that coefficient. That will be the constant coefficient, and then there'll be the linear term Rn, and then the coefficient p tilde u times 1 minus p tilde d. And then I'll match up. And I'll match up. Trying to compute here was this an plus bn times r. So here I'll find this is my an, and this here is my bn. So this gives me this recursion. I can express an and bn in terms of an plus 1 and bn plus 1, and I know where they end up. They end up at 0 and at 1. We could, of course, try to solve the recursions like we did before. We could try to solve. We could solve for an and bn. And I think the one that works is an being a sum from n to n minus 1 of bk. And the bn's are these p tilde u plus 1 minus p tilde d to some power n minus little n. And you can see that here because missing a term, right? Just bn plus 1 should be over here. Bn plus 1 is multiplied onto everything. So you can see that you get bn from bn plus 1 by multiplying here. So you can solve that. You're going to get some power structure. And then over here, you're going to get an. You're going to get an from an plus 1 plus this term here. So this is going to be a sum. So this is how the futures price process look like in a model where the terminal value of the futures price is pinned down to be Rn, and where the interest rate model has this form. How does that sound? Do you have any questions? On futures? I should just maybe go over it one more time. The first thing we did was to derive an abstract formula for the futures price process. And the difference between a futures and a forward contract is that for the futures, you have these running payments. At the forward, you just get a payment at the end. So for the futures, you get these running payments every single time point along. You're going to get a payment. You're going to take the number of shares. This is the number of futures times this price change in the futures price. So that happens at every single time point, right? And then at the end, the last futures price is pinned down to be whatever the futures is written on, so Sn. Right, we don't have that phi n here is equal to S at time little n. That's not true. You only match up at the end. Right, that expression we had in the example over here. Right, at the end, the futures price is equal to R capital N. But at earlier times, Fk is not equal to Rk. Right, there's a correction. AK and BK, they are not equal to 0 and 1. Right, it's only at the end that you have that property. Okay, so this is how it works, and then we set up a portfolio that has a price tag of phi n, and it ends up with this amount of money in the bank, right? So then, what is the price process, or what is the price of such a payoff? Well, this is the risk neutral discounted value. Okay, that must be phi n because this is what it costs us to get there. So this gives us the formula that is very, very similar to the forward price, but it has this one difference. So you're computing expectations under the risk neutral measure instead of under the forward. Are there any questions about this example here? If not, then the last thing I wanted to do was to look at a problem that relates the two. How does forwards and futures compare? Are they the same? Are they different? And the answer is it depends. So we try to work that out. This is example, what was it, 14. So let's bring up example 14. So let's bring up number 14. Yep. So we're looking at a problem here where there are stock prices and there's a binomial model. The assumption that is being made here is that the bank account's price process is independent of the discounted. And then there's another assumption here, which looks a lot like Jensen. So let me try to write down some of the key steps here. So the first one is that SN0 is independent of the ratio between the stock and the bank. So SN is the stock. And then the other assumption is that there is a strict inequality in Jensen. So let me write that out. Then what we denote by phi 0, this is the futures. And we denote by K0, this is the forward. Right, and you've written on this S. And so there are three possibilities. How do these numbers relate? Are they the same? Is one bigger than the other? Is what can you say under these assumptions here? Right, so SN is a stock. We're making the assumption that the discounted stock price is independent of the money market account. And then we're making the assumption here that there's an inequality in Jensen, right? So we should just recall, so here we should recall Jensen. Right, if I take an expectation of a function of a random variable, there's a relationship to what happens when I put it outside. Does anybody remember which one is biggest? Which one is biggest here?
First one.
First one is biggest. And this works when F has to be, anybody remember what the property is?
Convex.
Yes. Right, so here, the function that we're looking at is 1 over x. And 1 over x looks like this. And this is convex, right? Because you can take take 2 points, put a straight line in between them. Take any 2 points, put a straight line in between them. That straight line, all the points in between on the straight line, you're at or above the function. So this 1 over x function is convex. And so Jensen says that you have greater than or equal to, and here we're saying we want to have strict. So that's probably going to be important somewhere in the argument. Right, so we have a stock, so right, this is traded. Remember, when you have traded securities, the forward price simplifies greatly. Okay, so let's try to work out what can we say here. So we have the forward, we have the futures. Let's start out with the forward. So the forward says that at time n, you're going to have, if we go long, the payoff is going to be S n minus the forward, K0. Right, and then we're going to discount by the bank. This forward price is solving this equation. Right, that's a constant, and it's going to solve this equation here. So that's the same thing as saying what, that K0, and then the expectation of 1 over Sn0, that this is equal to, and then the discounted stock. And this is the same. Here we find the zero coupon bond. This is K0 times the zero coupon bond. And on the right-hand side, this is where we take advantage of the fact that the stock is a traded security. So discounted, you know that's a martingale. So you're just going to get the initial stock pricing. So that took care of K0. Now for phi0, it's a different story. That one is different. It's not given according to this formula here. So try to work out what the futures price is. So the futures price, we go back to formula we derived here in the lectures a little while ago. The price that we're hunting is phi0. Right, so we take n equal to 0 here, n equal to 0 over here. So we get that phi0 is this expectation of Sn0. So we have that phi0. This is the expectation of Sn. But that one is difficult because I mean, there's no discounting, so I cannot use the martingale property. So what comes to the rescue? Well, the thing that comes to the rescue is this independence. The thing that comes to the rescue is independence. So if I would write this here as Sn0 times Sn over Sn0, right, that didn't change a thing. That didn't change a thing. This was all good. I just multiplied and divided by the same thing. And now I can use independence. Right, so this is a special property. In general, you will not have this independence, but this is assumed in this exercise. And so I can now break it. That was the independence. Okay, and then what else can we do? Well, we have the first, and then we have the second. The second one was good because we know exactly what the second one is. Like the second one, this was at K0. That was into the forward. That was what was going to give us a forward price. Like this expression here, this is exactly K0 B0 N. So we have that phi 0 is equal to this expectation here times that guy. Okay, as I may. The only thing that we haven't used is this one. What we're interested in is trying to figure out, is there a relationship between phi 0 and k 0? Well, it apparently, we need to look at how the other two quantities, is it bigger than or smaller than 0? What is going on? So we need to figure out, is this, when I multiply it onto B0n, is this bigger than, equal to, or less than 0? Because that is going to determine how phi 0 relates to k 0. Okay, so remember what B0n is. And there's only one assumption left that we haven't used. So it has to be this assumption here that's going to give it to us. So remember what this one here is equal to. Well, that was by definition, this is the discounted, you take $1 and you discount it. You take the expectation. Right, and so this expectation here, this is strictly bigger than the one we have over here. This is strictly bigger than 1 over the expectation of Sn0. And so now we get it, because what? If I have phi, so I have phi 0 is equal to that expectation times k0 times B0n. And so if I replace the zero coupon bond by the inequality I'm going to come up here, you see the two cancel out, and I'll just get k0. Right, so here the futures price is the more expensive one. And it's strictly more expensive. But again, keep in mind, this is not something that is going to be true in general. It relied on a number of properties when we're looking at futures and forwards, both being written on traded securities price process. We had an independence assumption, which in general, this is not going to be true, that the stock discount is independent of the money market account. And it's also, this one here is more benign, because as soon as you have stochasticity, you're going to get this strict inequality. This one here is much more benign because it comes from Jensen. This one here is harsh, and it's also harsh to say that the contracts are written on something traded. All the examples that we have seen, you're using rates, right? And so when you're using rates, you will not have this simple formula down here, right? That expectation here is much more complicated to compute. But at least here's an example of a case where futures and forwards, they are strictly different. Yeah, are there any questions or comments about what we've done today? If this is not the case, then this is a good place to stop. Next time next time is going to be the last lecture, and if there's something you want me to go over again, you can just let me know beforehand. Otherwise, we're gonna continue. We'll do more fixed income instruments, and if there's time, we'll try to do some foreign exchange as well. But this is all I have in mind for today. Are there any questions or comments before we call it quits? Otherwise, I will see you the office hours this week, and the last lecture is on next Tuesday.
Thank you, Professor.
All right, I will see you guys later.
Thank you, Professor.
Take care.